All right, as we start this video, make sure you have your textbook out and open. You're going to need the textbook to follow along. So make sure you've got it open to, if you have the big book, it's chapter 12. If you've got the little book, it's chapter 1. Okay, we're going to talk about blackbody radiation. And it's one of the first of the kind of the three problems that people point to when they explain why classical physics had to be replaced by quantum chemistry or quantum physics. And so the three ones that we're going to talk about in this class are blackbody radiation, photoelectric effect, and the wave-particle duality. And in particular today, or at this moment when you're watching this, we're going to talk about the blackbody radiation. The first thing with blackbody radiation is, what is a black body? So a black body is an object that can absorb radiation across the electromagnetic spectrum, and more importantly, for what we're going to look at in terms of the experimental data, it will emit electromagnetic radiation. There is a perfect black body, and it's an idealized thing. The closest you can come to in practical things is the sun. The sun emits all possible light, not just the visible light we see. It emits gamma rays, microwaves, everything you like. Make sure you go pause now if you need to and check and make sure you know the order of the different radiation spectrum. Do you know whether ultraviolet has more energy or IR has more energy, for example? Another common example that's mentioned is heated metal. You know, when you heat metal in a forge, it glows, and so it's emitting radiation, and you can see the different colors. As you heat it hotter and hotter, it goes from being red hot, which actually isn't very hot, to blue hot, which is hotter, to all the way to being white hot. Okay, so now pause the video. Hit pause, go look at figure 12.1 and 1.1 in the textbook. Read the caption. Look at figure 12.2 and 1.2. Black body spectrum. Read the caption. Okay, now you're back. So now you should know what a black body spectrum looks like because you're looking at it in the figure, right? It's continuous. It is temperature dependent. The peaks shift to lower wavelength, higher frequency, as the temperature increases. Remember, wavelength and frequency are inverse. So this is experimental data. This is what it is. So you need a theory or a model to explain that data. Okay. Well, classical physics has a theory. What should a black body radiation spectrum look like? And you can see this equation in your textbook, and you should go and look at it. And now let's talk about a little bit about what I expect you to be able to get from an equation. When you come to an equation in the textbook, don't just skip it. It's PChem, equations matter. In this equation, I like to encourage you to practice saying these things out loud. And so the way I would say this is spectral density. That's what the rho, the thing that looks like a P here is. The rho, which is a function of, parentheses mean you say a function of frequency and temperature, okay, for a specific small set of frequencies, right? So we're looking at a little piece, a slice, is equal to, there's a constant, 8 and pi, usual constants, the frequency cubed divided by this, the speed of light cubed, times, that's the energy. You can think of energy as just being kT, it's proportional to the temperature, times again the slice of the frequency. Okay, so you ought to look at this and say, the spectral frequency is proportional to some constants, and most importantly, the energy and the frequency cubed. Okay, this is a continuous equation, right? And if we look at this, we ought to be able to plot. Whenever you get to an equation in your textbook, you should pause, hit, and literally pause in the video here, go to Wolfram Alpha or go to your graphing calculator. Make a plot of y, okay, this is y over here equals, don't worry about the constants, you know, set them all equal to 1. Nu cubed. What does a graph of y equal x cubed look like? And that's what the graph you'd expect to see. That's what this classical prediction is showing you. Okay, go do that. Okay, so we know that the classical prediction says that the spectral density is predicted to increase as the frequency increases. In fact, it increases as nu cubed, the frequency cubed. And the temperature dependence, which is there, is carried in the average oscillator inches. So E equals KT. So there is a temperature in there that I haven't been talking about. So what you should have seen is that the classical predicts this sort of dotted line here, straight up. Okay? But that's not what the experimental data is. The experimental data says it goes up, but it comes back down. So we say that the classical is okay at low frequencies. See, this is 10 to the minus 14, so these are small frequencies. And it gets worse at high frequencies. It gets more and more wrong. And this is called the ultraviolet catastrophe. Why ultraviolet? Well, because higher frequency is ultraviolet light. It's beyond the visible. It starts going wrong at the ultraviolet. Okay, so what do I want you to do? I want you to be able to look in the book, start looking at the figures. You have to be an active reader. You have to pay attention, mostly in the P-Chem book, to the equations and the figures. Okay, you can look at the text, but most everything you're going to need to know is in the equations and the figures. And then we're going to talk about in class how the quantum gets a better model than the classical.